right, so help me remember. Can anyone tell me the effect this matrix would have on, if I apply it, if I multiply another matrix by it?
Row 1 would stay the same, row 2 would stay the same, and row 3 would be row 2.
Careful, no.
Column.
Which row changes? Second row. And what will the new second row, can you guys, what kind of matrix is this? What do we call this matrix? Elementary matrix.
Are you multiplying on that side or that side?
Ah, good point. So that's why I think I was specific. I said if I apply this, if I multiply this by another matrix. Because you're right. It's kind of like where I'm going later tonight, is the difference between sides. So does everybody see the effect it would have? Which row would change? Row 2. And how exactly would it change? It would be the old row 2 plus row 3. You guys see that? Can you guys see that? Okay. There is a special class of, so with whatever matrix I put here, what's got to be true about its dimensions? This, of course, is 3 by 3. Give me one dimension that would work here. 3 by 1, 3 by 2, 3 by 3, 3 by whatever, right? Keep up. I'm going to stop for a minute. You guys with me? That's the basics of multiply matrices. The inner's got to match, and the outer would be how big the answer is. Yes? Okay. Like it. There's a certain class of these matrices that don't deal with just combinations and multiples, but they deal with changing order of rows. And there's a certain algorithm I could apply. If I have the numbers 1, 2, 3, and I make them 1, 3, 2, I've just applied a certain idea. I don't know if you guys know what the idea is. If you took any statistics, there's combinations and there's something else. Permutations. Permutations were the ones that count things in a different order more than just once. So like if I just needed 3 people to come with me, I wouldn't say that you, and you is different from you, and you. You're the same 3 people, yes? But of course, if I were to pick a president and a vice president and I was going to say something else. I was going to say, something about those. The person in charge of finding imaginary fraud. No. Speaker of that, sure. Then it would matter the order I state them, yes? And that's what we would call permutation. So permutations is all the different ways I could reorder something. So if I wanted to reorder a given matrix, if I wanted to make row 2 and row 1 switch, how do you guys think that would be represented in my permutation matrix?
0, 0, 0, 0, 1.
Do it again, D. So I want to make, what did I say? I want to make row 1 and row 2 switch. Do it again. 0, 1, 0. 1, 0, 0. 0, 0, 1. I like it. And so that is, you could call it a type of elementary matrix, but it's not, because an elementary matrix is specifically relegated to multiples and combinations. So permutation is kind of like another side note. It's like, oh, you could also switch the order of the rows. Okay, and again, on one level, this is almost a little silly. But again, one big thing that we use linear algebra for is creating programs. If I can put a bunch of permutations together into one big matrix, I can apply it to several different things. I can look at it as a subroutine. We're going to do some theoretical stuff with it, which is important. So if you kind of started to do this, can you guys see how it does do what we want it to do? Because if I do 0, 1, 0, it's just going to pick these out. Do you guys see what I mean when I say that? 0, 1, 0. So it's just going to pick these out. And then 1, 0, 0 is just going to pick these out. And of course, the last one is going to just sit there going, what are you guys doing? Okay. what do you think the inverse of that is? Let's call this P1. What do you think the inverse of P1 is? This might be a little weird, but what do you think? How would you undo that switch? I guess I could be a little more. I think the book goes back and forth. Let's call this P12. Sure. Let me see if you guys are really with me. Y equals 1 over x. Y equals 1 over x. What's the inverse function of that?
X equals 1 over 1. Or y.
Which is?
It's still the same.
Y equals 1 over x. And how do you undo flipping something? Flip it again. How do you undo flipping the first and second row? Flip them again. So isn't it its own inverse? Okay, I like it. How would you verify that?
Multiply it.
Yeah, good. If you multiply it by itself, what should you get? If that's true, what should you get? Identity matrix. I love it. Okay, so let me slow down for a second. So we have the idea of permutation matrices. The more general idea, very quickly, just make sure everybody's really with me, is I can look at a matrix as a collection of commands. Do this, do this, do this to a given matrix. Yes? Elementary matrices are easy to see because they only do one thing at a time. Permutation matrices only do one thing at a time. But every matrix you can ever make is a list of commands. It does specific things to another matrix. It will do the exact same things to every matrix you feed to it. You just have to know what those things are. Yeah? So this second matrix I wrote is not as easy to tell what it does because there's a lot going on, yeah? Maybe. Okay. So what about here? What would this do to something? Does anything stay in the same place? So what does that do? Puts the first row second. Puts the second row last, and puts the third row first. I like it. Are you guys with me? This is still a permutation matrix. It just happens to be doing a few things. So a good question then is, I've already shown you 2 possible permutation matrices. How many total are there for a 3x3 matrix? How many permutations are there?
9, 6.
Ooh, we got, yeah. So why do you say 9? Why do you say 6? There's 2, I heard 2 things.
Factorial 3.
Sure, 3 factorial kind of comes into play. Real quick question. How many guys know this notation mathematically? This is not 3! What does that mean? What does that mean? Do you guys know?
3 factorial.
Which means what?
Which means 1 times
3
2.
times 2 times 1, or 1 times 2 times 3, yeah. Depending on the situation. Now, if you ever taken, well, all of you should have taken Calc 2. Y'all know this shit. You've seen this stuff in its final form almost, right? You've seen like 2n minus 3 factorial, or even double factorial possibly, depending on your teacher. Any of you guys ever seen double factorial? All right, let's not go. So factorial just means start with that and multiply down. So what about 1/2 factorial, out of curiosity? Let's say it.
Yeah.
Gamma function, I love it. So this is a specific application of something called a gamma function. We won't talk about it. I wanted to see if anybody knew that there is a definition for that, because there's a broader definition of this idea that the factorial builds on. All a side note, I'm sorry. Okay. So factorial is going to come into play. Let's go back. Do you all agree that there's 3 rows? 1, 2, 3. So it really is the same idea as how many ways can I reorder these three numbers? That's the same thing as how many ways can I reorder those three rows. Do you agree? Same problem. Counts are the same in each problem. So how do I figure out how many ways there is to reorder 1, 2, 3? Well, how many numbers could I put in the first place? If I'm going to reorder 1, 2, 3, how many numbers could I put in the first place? Okay, I put a number in the first place. How many numbers could I put in the second place? I'm reordering. I'm not cloning. I'm not rewriting. So there's three. I want you guys to really understand what I'm saying. There are three numbers. Could you put 1, 2, or 3 first? Yes. So if you put one of those down, how many options do you have now for the second number? 2. Isn't that exactly the idea of factorial? 3 times 2 times 1. So for any given matrix size, n by n, we're going to focus on square matrices for now, there are n factorial permutations. Now, that is including one that you might not think to include. And that would be the permutation 1, 2, 3, which is effectively the identity matrix, which is just leave it alone. But isn't that a way to order things? Hey, can you order 1, 2, 3? You got it. 1, 2, 3. Thanks. So don't forget that actually includes the identity matrix itself. Okay. I love you guys. So if I had a 2 by 2, how many possible permutations are there for a 2 by 2? You do it 2 ways. What's 2 factorial? 2. And if you and here's one, the leave it alone option, and then the other option is so there's only 2 ways to reorder to permute a 2 by 2. Okay, I like it. Okay, good. Okay. So one question you might be asking is, what the shit are we talking about permutation matrices for, Jeff? Well, one thing is, geez, don't talk to me like that. But no, the other thing is we've used permutations already. We just didn't call it such, yes? When we row reduced, didn't we at some point, didn't we switch rows? When we were doing row reducing, yes? Because we wanted it to be a non-zero pivot. So I think Strang brought up the idea of a pivot matrix before he discussed pivot matrices, which again, is his superpower. So to formalize what I just said, for any given invertible matrix, there is a permutation matrix that might be compositions of several instruments. There is a permutation matrix such that when I do our LU factorization, yes, like we had to do on the test. And by the way, in general, if I show you a way in the class, there's also a way the book does it. You can do it either way you want to. So I love the fact that some of you guys did it the way the book did it. Tears. Yes? When I do this craziness, if I apply the permutation first, what might I avoid that I don't want to let happen? What's the worst thing to get when you're trying to do LU? Zero pivot. And of course, now on one level, this whole discussion is silly as shit because you just freaking do this, Jeff. Yeah. So on one level, you're like, I'm just going to switch the rows if I get a zero pivot, and if I can, yes. But we're always in the back of our mind thinking, these are kind of things I want to be able to program into like a little subroutine that would just do it automatically when it solves things. And I think I mentioned to you guys, if any of you are going into programming stuff based on linear algebra, when you are row reducing a matrix, you start with the largest pivot. When we're doing it, us humans, we start with any ones we can see, yes? If you start with the largest pivot, that's the safest. You have the least likelihood of creating zero pivots, meaning pivots that are zero, yes? You get fractional stuff, but does a computer give a shit? No. Humans, we use ones because we give a shit about the numbers we get. Computers use the biggest pivot possible. because it cares that it doesn't have to do a permutation. Okay. Maybe. Blah, 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 blah. Oh, let me not forget any of these little things. If P is a permutation matrix, P inverse is also. In fact, specifically, it's the permutation that undoes this permutation, so it only makes sense that it is also a permutation matrix. P1 times P2, blah, 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 is also a permutation matrix. This is all very nifty stuff. I'll call it a perm matrix, why not? And I already said this third one is, if A is invertible, I don't know how you want to put this, all this little discussion up here. There exists a P such that if you multiply it by A, you can get it so that you don't have to switch things so you get a zero pivot. Yeah.
Is the reason it's PA equals LU instead of like A equals PLU?
Yeah, because you apply P to A before you do the LU process.
Oh.
So the idea is there exists a P so that if you applied it to A first, the LU process wouldn't require a permutation. Now, in practice, what do? We apply the permutation as we need to, right? Is that cool?
Yeah.
In a computer program, I would apply a permutation that would put the largest pivot in the first spot, for example, and then I would start the process. Does that make sense? Because again, in general, if you start with the largest pivot, you have a smaller chance of making a zero in your other pivots. Love you guys so much. Okay. Bump, bump, bump. Now, coming back to what you said earlier, I think over here, somebody. Let's just do. Yeah. All this has to be is 3 by something, yes? So just to get the point across, let's just do 3 by 2. Okay. So without actually multiplying, what would happen here? I mean, or if I did actually multiply, it doesn't matter. You can see very quickly what's going to happen. Yes? What will happen? Can somebody just tell me without actually multiplying? What should go first? Second row. And if I multiply, I get 0, -2, 0. Yeah, so the second row is going to show first. Third row next. First row last. I love it. What did I mess up? That's my time. Oh, I put the second row. I don't know why that's messing me up the music. Oh, here we go, Chuck. First row last. There you go. What if I do, what if I beef this up a little bit? And I apply this same matrix on the other side. Somebody had mentioned that earlier. Why do I have to beef that one up a little bit? Because what size is this? 3 by 2. So if I put a 3 by 2 here, it would never work with a 3 by 3. I'm doing the same matrix, but on the other side. Yes. You guys all with me? Okay. But so, what will happen now? And this is related to the idea of the row space and the column space that we did way long time ago. Either the dot product approach or the combination of columns approach. Let's just multiply this out. Let's see what happens. The beautiful thing about multiplying this out is there's a lot of zeros. So I'm going to get 0, 0, 3, yes? You with me? Let's just do it blindly. And then I get 1, 0, 0. And then I get 0, 2, 0. You guys all with me? This will come up with 4. Is that cool? This will come up with -2. This will come up with 3. Will come up with 1. Will come up with 4. Will come up with -5. Is that cool? Just seeing which part gets the 1 because it's the only one that's left alive. Can anyone see what actually happened? Column swap. So if I multiply a permutation matrix on the other side of A, so this would be what we call PA, and just to be snarky about it, we call this A cubed. Same stupid matrix, but we just give it a little different letter. I'm trying to keep in same notation as the book. It's the same exact matrix. If I multiply it at first, if I multiply it on the right side, on the left side, I'm trying to think about yours. If I multiply it on the left side, it'll change the rows. If I multiply it on the right side, it'll change the columns. There it is. Okay. Oh, I did that one. Beautiful. Okay. How are we doing there so far? There's one thing I meant to do earlier. Let me see if you guys can go with me on this. If I have this, let's call this just P. What would P squared be? What do you think P squared is? P times P. So if we multiply this P times this P itself, and again, you could either do the multiplication or you could just realize what it's doing to itself. I don't know if you guys can, it's a little bit trippy when you're seeing all the same numbers. But doesn't this say to take the last one and put it first? Yes? Take the first one and put it second. And take the second one and put it last. Isn't that what it says to do? And if you multiply, let's see, you get 0, 1, 0. Do you guys see what I'm saying? You could either think about what this actually permutes on this, or you can think about just multiplying it out and going slowly and saying, okay, maybe. Let's check it out. What does this say to do to these columns? Think of this as Q now. This says put the first column, this says put the first column last. Did we? Did we put the first column last? Yes. It says put the last column second. Did we? And then put the, what did I miss? Third column, wait, I forgot now. Damn. Put the first column third. I think I already did that one.
Second column first.
Thank you, I'm so tired, I'm sorry. Yeah, so if I look at it either as this guy acting on him columns or this guy acting on him rows, it'll work either way. Now, have we gotten back to the identity matrix? Is P squared equal to P? No. Okay. What's P cubed? Let's see if you guys are cool with this. This will be, P cubed is a little weird. This will be P times P squared so I get, just doing the multiplication real quick, 1, 0, 0, 0, 1, 0, 0, 0, 1. Did I get back to the identity matrix? Yes, okay. So we call this permutation, we call it an odd permutation because it takes 3 of itself to get back to the identity matrix. So it took 3 applications of that matrix to get back to the same matrix at first. You back to the identity matrix. Okay.
Would it be even if it was just?
If it only took 2 or 4, would it?
Yeah.
It'd be even. Okay. Oh, that's right. Yeah, he's great for this. Okay. So something that's come up earlier in the book, and I don't think I've addressed it yet. Nobody's asked me about it, but I'm pretty sure it came up in one of the earlier sections. Has anyone seen something that looks like this? Okay. Did any of you just sort of go, that doesn't seem to be too important, so I'm just going to forget that I saw that? Or did anyone actually look into it? If you didn't look into it, I don't blame you. Did you look into it? Did you find out what it was?
Yeah, it's the transpose.
Transpose.
It's a-
Kick ass. So I thought for sure it had come up before, and I think I warned you guys, and I do my best to catch where this happens. He will bring up ideas that he has not discussed yet. So he's talked about transpose sort of notationally before without telling you what it was. If any of you guys have ever used Excel much before, you've probably done the transpose of an array of data. All a transpose does for a matrix is it takes all the rows and makes them columns, and or vice versa, right? If you take all the rows and make them columns, then you took all the columns and you made them rows, all at the same time. Does that make sense? So, for example, just to look at this by itself, you just read it as A transpose. If A was 1, 2, buckle my shoe, -3, 5, what is A transpose? A transpose. Yeah. Take the column, make it a row, or take the row and make it a column, or take the row and it doesn't matter any way you do it. What's going to go here no matter what? 5. So take this and make it a column, or take this and take this and make it a row. It doesn't matter what you do. Okay. I like it. So what in the world, okay, let's go back in time a little bit. If P is, let's see, I don't want to say this. Sure, we'll do the same one we just did a minute ago. Here's what's really trippy. You don't have to do a lot of work to figure this out. Okay. For a 2x2 matrix, do we have a shortcut to get the inverse? Yes, and that's part of what I tested you on. Some of you guys forgot. You did the Memorex, the augmented with the identity. I didn't say you had to do it a certain way, so that was fine. So in general, I could augment this with the identity, but does anyone notice something we just did a moment ago? We actually already calculated what P inverse was for this specific P. If something is the inverse, what happens when I multiply it with the original? I get the identity. Did we just multiply P by something and got the identity?
P squared.
And what was P squared?
0, 1, 0.
Sorry, hold on.
0, 0.
I got it somewhere. What'd you say?
0, 1, 0.
Yeah.
0, 0, 1, 1, 0, 0.
Okay. Is everybody with me on that? In this specific instance, we happen to already do work that showed us what the inverse was. Can you guys take a moment and right here write P transpose? What are you guys getting? So if I take the first row and make it a column, take the second row and make it a column, make that a column. Yeah, so this is actually generally true. P transpose is P inverse. Always. Just good to know. Trying to figure out what order to do this next stuff in. Let's see. Yeah. I don't want to do that. Oh, we already did that. Beautiful. Okay. Oh, okay. So let's do this. We'll do this next. Yeah, guys, that's a little weird. We'll do that one later. What do you think about AB transpose?
You do A times B and then take its transpose.
Sure. That's how you calculate it directly. But what is, for example, what is the quantity 2x squared?
2 squared is...
Yeah, so 4x squared, yes? You with me? So there's a way to rewrite, in that case, that's a power. T is not a power, it's a, we chose to put the T up there, but we know it just means transpose. So I want to know, is there another way to write AB transpose without the parentheses?
A transpose.
And you would think that maybe you just distribute. Yes. So let's figure out why that might be true. Okay. So in reality, what happens is AB transpose, no Jeff, is B transpose A transpose.
What is B A for?
We'll figure it out.
Okay.
Yeah, sorry. So I wanted to write down the actual idea, and then let's explore it right now. If we start with like, let's start looking at this instead. Let's look at this. Oops. Let me see if you guys really paid attention earlier. Not just because I used the letter P, but that matrix, what will it do to A? Will it mess with its rows or will it mess with its columns? The rows. You guys with me? If I would have put it second, I don't care if I call it P or Q, what other shit, it would have messed with the columns. You guys with me? When I say messed with, I mean reorder. Yes, reorganize. If I transpose A, the rows and the columns switch. If I transpose A first, would it make sense? Why does this not make sense? Don't even write this. This is so wrong. Why does this not make sense then? Because this would mess with the... Yeah, so I would need this to be A transpose B transpose. Maybe. So that's kind of like the first level of understanding what's happening. What's a nice quick... Oh, of course. If I expand on this, let me see. If I think about an elementary matrix applied to a matrix, and I want to transpose those, a very similar thing for the same reason would happen. In every matrix that exists is a multiple of E's and P's. I don't know if you guys are really with me or not. If I do enough elementary, if I start with 1, 0, 0, 0, 1, 0, 0, 0, 1, and I do enough elementary matrices to it, could I make it into any matrix I want it to be? Okay, therefore any matrix in existence is a combination of E's and P's. Good. So which means if I have A times P, E, P, P, E, P, P, I could just collect that and call it B. In which case every time I do it, it's going to get this, so I can just kind of summarize that as the result should be the other way around. Now, we could do specific concrete examples of this, right? We'll do one just to kind of show you, might as well, just to really verify. Let's say that A is, let's just make 2 by 2 just to do this quickly. 2, -3, 1, 4, and B is -1, 3, 2, 1. I want all of you guys to do A times B and then transpose it. I want all of you guys to do B transpose A transpose and then multiply them, yes? And then I want you guys to do either of those. You get to pick. Why did they get to pick? I don't know. Because I only had 2 things and I got 3 groups. What do you want from me? And what am I going to do? I don't know. I'm going to freeze this so you can't see what I'm doing. My hand is going to stay there forever. Bum, bum, bum. Now you're like, if I could just add, that would be amazing. I really want us to go through this just so I can point out the math that happens. If I could write, that'd be great. All right, let me see. How about this group of, has anybody done? I wanted you guys to do AB and then transpose it. Yes? What'd you get?
-8737.
-8737. And then I wanted you guys to do B transpose and transpose and then multiply. What'd you guys get? Ruh-roh, something went wrong. Should get the exact same thing. Did anybody else get the exact same thing? Ruh-roh, okay. And then you guys, you did whatever you wanted to. So, AB is this, yes? I know the middle row, just the middle column, sure, you guys are a big matrix. And then you transpose, you get there. Middle guys, what is B transpose? Yeah, -1, 3, that like this way, right? -1, 3, and then 2, 1 this way, yes? And what's A transpose? 2, -3, 1, 4, like that, yes? So if you take this first and this second, you should get -2 minus 6 is -8. -1 plus 8 is 7. 6 minus 3 is 3. 3 plus 4 is 7. Yes? You get the same thing. Now, real quick. Do you see how up here you did 2 times -1, -3 times 2? Yes? Let me see if I can show you. And over here you did 2 times -1, -3 times 2. Just 1 is now a column when it used to be a row. Okay, I need you to see this. So when you did A times B, you did 2, -3, dotted with -1, 2. Down here we did -1, 2, dotted with 2, -3. Yes? Same thing, correct? Do you guys see? Again, how transposing works will of course affect what side the matrix should be on to capture the same thing you got before. Because now when I try to do the dot product, what was a row is now a column. So of course I've got to turn them around to have the same output. Do you guys, I could have done a 3x3, that would have taken a little longer, yes, but it's the same idea with a 3x3. I still have the same idea of, I want the same dot products. So if I switch the rows and columns, I must switch which matrix comes first so the correct row and column match up again. Does that make sense? Because I understand it is not immediately obvious why the transpose should make them turn around. But now when you realize the way we've defined the way that we do this normally is the dotting of the column with the row with the column, that's got to be preserved. Okay, I like it, I like it, I like it. You would, Jeff? Eat. Sorry. I'm hungry. Okay. Let's see. Ooh. How much time do I have? 7 minutes. Neato. Did somebody change the clock? I didn't want to do too much today anyway, considering I am silly, stupid, tired. Just do one more thing. I love you guys so much. What about this? Of course, that's what that says to do. What do you think this could potentially be? No, careful. If it was P, I would agree with you. Because P transpose is the inverse, right? So what's P inverse transpose? It's P. Is that what you guys are thinking? Yeah. A inverse could be any frickin' thing, yes? Couldn't A inverse have fractions when A didn't have any? Of course, I'm divided by 1 over AD minus B, by BC if I'm doing a 2 by 2, yes? 3 by 3, forget about it. It can be all kinds of weird shit, yes? So there's no reason I should expect this to necessarily do anything, but somebody back there is telling me to, I think he's telling me to bunt? I don't know. Let's give me some kind of signal. Do you think it's this? Intriguing. So I'll tell you this. I want at least one of you to create a matrix A and just play with it. Just see what happens. If you find the inverse and transpose, or if you find the transpose and then invert it. Do it on your calculator if you want to. Just play with it. Try to see if you can see a pattern to the results. Are they the same? Is one half the other one? Are they not related at all? Right? Yes? Now, and a quick, broad, general statement about calculator usage. On the test, there was that one problem where you had to make it CR, so you had to row reduce it. There were 2 steps. No, you can't use your calculator for that. Come on. I will be very explicit when I don't need to see any work from you. Now, some of you guys realized if you just identify which column is dependent on which other ones and how, you could build CNR. Tears. That's awesome. You don't have to row reduce if you don't want to, as long as you show me thought process. Don't just say, well, I clicked this button and I got this. No. That's no good. No. You guys got it with me? There will be times when I will let you use a calculator to get A inverse or whatever the shit, because that's not the point of the problem. We just need it to continue. You guys with me? That problem was partially me making sure you know how to row reduce and partially me making sure you know how to put it back together. All right, that's enough. Okay, all right. So play with this. Next time I'll ask if anybody's figured something out about that. We're about to get into chapter 3. And I think I told somebody earlier, because we don't do 2.5. Chapter 3 is sort of the place a lot of books start. Because this book is really organized in a very different way. So we're going to get some more concrete stuff in chapter 3, yes.
So what was 2.4?
We just did 2.4, yeah. Permutations, transposes, that's 2.4. All right, guys. I'll see you guys on Wednesday.